Okay, so lecture 12 of Dynamical Systems. Today we're going to continue looking at conservative systems, like the ones you have in your problem set. And we're going to look at, in particular, the pendulum. And the pendulum is important because it's a very simple physical system, but it also is a set of equations that appear again and again and again. It's like the simplest example that illustrates a number of other things that we also get in conservative systems. And then later when we start doing chaos, we actually do an equation that's very closely related to the pendulum equation, and we study that. Okay, so it's an important foundation step. So just, if I can start it speaking to me. Okay, so the simple pendulum, you basically have the situation, you have mass M, the little green mass over there. It's attached to a rigid wire, in other words, that wire can't bend. It moves under the influence of gravity, the length of the wire is L, and it experiences gravitational attraction, which is straight down, and so the thing is restricted to moving with a rigid wire, so the forces experience can be broken down into two parts. The one is this one that is in the same direction but opposite to the wire. That's exactly balanced by the tension in the wire, so we don't worry about it. The second one is a residual force over here that's just g sine theta that then basically causes an acceleration because there's nothing restraining it. And the force balance equations, in other words, that the acceleration is merely equals to the acceleration in this way, you can break it down in components, and what you're eventually left with is in the theta direction, in other words, this direction over there, you have that it's basically the acceleration in this tangential direction is just equals to this component of the force, so it's just equals to g sine theta. So those are the equations that we're going to be looking at, and you can immediately see that here once again are two parameters in, and because we're mathematicians we want to look at it as in the simplest way as possible, and the way we do that is to non-dimensionalize. And we've non-dimensionalized before. Remember, the things that you can do is you can rescale your time, you can multiply the equations by a constant, you can rescale the variables, and you can rename the constants. Those are the three things that you can try, and we did in a previous example, and here's another nice way. So what we're going to do is we basically want to get rid of these constants over there. So the one thing you can do is you divide by L, so it's G over L, so we effectively have one constant that we're going to want to get rid of. And the way we do that is we can introduce a new time called omega t and choose that wisely, and then we can get rid of all the constants, in fact. So what we do is we introduce a new time that we're going to call tau, which is equals to omega t. And what that eventually means is that the derivatives with respect to t is just omega times the derivatives with respect to tau. So if we now substitute that into the equation, what we get is omega squared L times dd tau squared of d theta, the second derivative of theta with respect to tau, plus g sine theta is equals to 0. And now we want to get rid of all those constants by choosing, because remember we can choose omega as long as we don't choose it to be 0. We choose omega squared equals to g over L, and we divide the whole equation by g, and then what we're left with is that. Okay? So what you can now do is you can analyze this equation completely with no constants. And then if you want to get back the actual physical results in the real time, you work out what omega is, which is just the square root of g divided by L, okay? And you just rescale the time, and then you have the physical answer, okay, for theta. So it's the basic statement is the physics or the way it behaves is not dependent on the constants, but if you want to get it into a real scenario, you basically have to rescale the time by a set frequency that is set by the gravitational constant in L. Okay, so if you're on the moon, different length pendulums will the same length pendulum will behave differently on the moon and on the Earth. Okay, but the basic means in which it works will not change. Okay, so just the timing of how rapidly it swings, it's going to change, but the actual physics of what happens and the dynamical properties is not going to change. Okay, and so what we're going to do for the rest of the lecture is analyze this equation. So the first thing you can observe, okay, and just to remember, the dots in this case is derivatives with respect to the new time tau. Okay. So the first thing we're going to do is write it as a first order system, and that you should by now be familiar with. You basically say V is the dimensionless angular velocity, which is basically how rapidly this thing is turning, and V dot is equals to minus sine theta. Okay, that just comes from the differential equation. And then you go about doing the normal thing. Fix points, linearize, and then you do the additional fancy tricks. Okay, so the fixed points are when V squared is 0 and sine squared, sine of theta star is equals to 0. That immediately means that this is true whenever theta star is equals to n pi. Okay, so you write down, and this is important, you write down all the possibilities. You're dealing with mathematics, not physics, so you want to write the full series of solutions down. Okay, so n pi, and then you say n is an integer, so you give all the details. The next step you want to do is examine what the equation looks like at all the fixed points, and you work out your Jacobian. And so it's simply dd theta of this first equation is 0, dd v is 1, so there we go, the 1. dd theta of this minus sine theta is just minus cos theta, and dd v of sine theta is 0. So that's our linearized equation. You work out the determinant and the trace at particular cases. So now, if n is even, right, then the fixed points for the even ones, you have that a is equals to 2m pi 0, and that's equals to 0, 1, minus 1. So in other words, at the fixed points 0, 2 pi, 4 pi, etc., you work out the determinant, which is equals to 1 and it's greater than 0, so you immediately know it is not a saddle. You work out the trace that is 0, so you know it's a center. Okay, and it's a linear center, you know nothing more about it at this point. You then go out and you say if n is odd, in other words, it's like pi or 3 pi, then you work out, then the matrix has this form. Okay, so cos of an odd number is just minus 1, or an odd multiple of pi is just minus 1, so the matrix is that way. You immediately work out the determinant is less than 1, so you know you have a saddle. Okay, so this you can do for any system, and you should already start getting clues that you can write down a conservative potential for this function. One, because it's of the form that we actually derived it for in general. In other words, x double dot is a function of x. But two, you've seen in your linear analysis, remember that you only get centers and saddles, and this is indicative of a conservative system. So you can start suspecting that there must be a thing. And even if it wasn't in this reasonably easy form, if they'd chosen another set of coordinates in which it looked bad, if you still get centers and saddles, then you suspect that there may be a conservative constant, even a conservative function, even though it's not obvious that it's this x double dot is equals to a function of x thing. Okay, so that's your linear analysis. You always do that. The next step is we want to plot the phase diagram. Okay, so we're going to plot the phase portrait. There's once again our linear system. We're basically going to put like the double well, we're going to put on all the details that we've done in the past. So we've done our linear analysis, we immediately put it on the plot. So we're going to plot all the fixed points, right? So there's the fixed points, I've just made them bigger. All the even ones is where, and there is where we get the linear centers. So I put little circles around them so I already know that they're linear centers. These odd ones are where the saddles are. So then we can plot the eigendirections for the saddle. And because the matrix is just 0, 1, 0, 1, 0, 1, 1, 0, the eigendirections are reasonably simple. We've worked them out before. You have the unstable eigendirections where the eigenvalue is positive. They point in the 1, 1 direction. And you have the stable ones where it's coming in that point in the -1, -1 direction. Just one thing about this graph, I haven't made the scales the same. That's why these things are a little bit squashed, even though they're actually pointing in the 1, 1 direction, right? I've got this is about 6, and I'm going to have about 4 on that axis. So I've squashed it to fit it in. Okay, so we've got our stable and unstable eigendirections. The next thing we do is we plot the null clines, right? The first null cline is when v is equals to 0, and we put the arrows on, because they're always vertical when theta dot is equals to 0. The change is just in the v direction. The second null clines is whenever sine of theta is equals to 0. So for every single fixed point, we're going to have another null cline going through there. And because when v dot is 0, theta dot is just equals to v, you get the same set of arrows at every single 6 points, and you put it in because it guides you, especially if you're going to plot it by hand. Right, so now the next thing is we analyze the symmetries, because it will help us do the phase diagram. And here is an unusual one. These equations are 2 pi periodic in theta. In other words, if you were to go and you replace theta with theta plus 2 pi, the equations are unchanged. Okay, so what you expect then from the phase diagram is that this part, say from 0 to 2 pi, is going to look exactly the same as minus 2 pi to 2 pi. So in actual fact, I'm plotting double what the phase I need to plot of the phase diagram. Okay, it's just to illustrate to you exactly how it happens. But it's something to remember. The second one is that you have this symmetry. If you change theta to minus theta, t to minus t, basically reverse the arrows, and v to v, it's also going to be unchanged. And that basically means that above and below, there's going to be a mirror image of each other, just with the arrows reversed. And the say above and below the v equals to 0 axis. The same is true, sorry, no, not above and below. You change theta to minus theta. So left and right, the two things, if you flip it above about 0, the two things are going to remain the same. The second one basically gives you above and below are going to be the same, just with the arrows reversed. So if you start plotting things that don't have those properties, you're making a mistake somewhere, and you've got to check where it is. Now, we know we have a linear center. We know we have saddles, so that gives an indication that we must look for a conservative quantity. And for this particular example, I derived the general conservative quantity is associated with the equations. It's simply the integral, the potential over here is simply the integral of the force up at the top. So you have a half v squared plus cos theta. So you basically have the effectively, in physics you'll view it as the kinetic energy plus the potential energy remains constant for a particular orbit. In this case, it's just a mathematical thing that obeys the property that along the trajectories E dot is equals to 0, and we're simply going to check that now. So I usually check that I've got the right thing and that I haven't made a stupid sign mistake by simply working it out, and I advise you to do the same. Okay, so we have E dot, that's basically the derivative with respect to tau of this thing, so it's VV dot plus the derivative with respect to theta of that thing. The derivative of cos theta is minus sine theta, so we're left with sine theta, theta dot. We go back to these equations up at the top and replace what theta dot and V dot are. Okay, so we have V dot is simply minus sine theta, and theta dot is simply V, and we see that there's a sign difference, and they cancel very nicely. So we've just proved that it's conservative, which is great because we can now have a method of plotting the full general phase diagram beyond the information we just already have from the linearization. What we also know is that because this thing has a local minimum at 0, 0, okay, E has a local minimum at 0, 0, you can work that out by simply working out the gradient, and working out the second derivatives, we know that we have a nonlinear center over there. So our linear centers are nonlinear centers, which is typical of conservative systems. Okay, and just to sort of give you another way of looking at this, a way of proving that also is to Taylor expand. So for small theta, you can say your energy is equals to half v squared, which is just the first term, and then you Taylor expand what cos is, okay, and then you just group them together, and you have that it's basically your energy is minus 1, which is just a constant, plus a half theta squared plus v squared. So that then gives you a proof that it's little circles, right? If you think of a potential of some function equals to x squared plus y squared, that just gives you a whole bunch of concentric circles. So it's just another way of proving that you have a nonlinear center over here. Right, so now the contours are circles, and now we want to plot the full diagram, okay? We also have from this equation that for a fixed energy, which is how we characterized our orbits, we have that V we could actually write down the formula for, and this is now what we're going to use to plot the general phase diagram. And so how we go about it, it's very similar to the double well potential. We go and we plot the potential up at the top, which is just the integral of the force for these type of equations. And we put it in. We know that we're simply plotting, minus cos theta. So we put all the places at which cos theta goes to 0, which is just pi over 2 times some constant. We put in all the places where it reaches maxima. Okay, and so basically maxima and minima, so it's minus 1 and pi, so you can see how my scale is not exactly square, and we put it in. And now we go on and we say, let's pick an energy and plot that particular energy contour. So the energy we pick is, say, let's start up here. The first thing you can see over here is that there are no fixed points. In other words, there is no place in which basically you have that E minus V squared is equals to 0. Okay? And the only thing you can use to draw this contour is you basically look at the extremis. So down here, the V is basically a maximum because it's basically equals to 2 times the square root of this distance. Okay? So you can go and you can put all those points in. You simply take 2 times the square root of 1.8 plus 1, so it's 2 times the square root of, it's the square root of 2 times 2.8, and you work out the value and you put it in there. So 1, and the same is true over here, 2, 3. The next thing you can work out is this minimum distance over here. So this is basically just 2 times 0.8 square root, and you put it in over there. So they're both positive. There's nothing that goes to 0 below the square root. And you then just draw in something that has the maximum and minima over there. And you know, because you're hitting a null line over here, the arrow is horizontal, so you must basically have a turning point over here. You're hitting another null line over there, where the arrow is also horizontal, you have another turning point. So given these points, you can actually draw the thing. What you now are going to do is you're going to use the symmetry to draw the one below. Okay? Just for interest's sake, what does the solution represent? You have a pendulum, it can do this. But if it doesn't turn around, it can do, sure, that was painful. It can do this, okay? So that solution is the one that's the whirly solution that whirls around. And it can whirl around one way, and you hit the box, but it can whirl around the other way as well. Okay, so it's the two solutions, the top one at the top and the bottom one below. So the next step, let's reduce the energy a little bit. So we have that one, still no fixed points over here. Okay, so it's still a whirling solution. It's just a whirling solution where the velocity is lower. You do the same thing. You plot the maxima, which is this distance times 2 square root. You plot the minima, which is this little distance times 2 square root. And you put it in. You use symmetry to plot the bottom one, and you put it in as well. Just one comment, if you're plotting these things, it's usually good to put arrows that indicate what the flow is like and which way it's flowing. Okay, here you can get the arrows from my vector field, but I prefer it if you just put them on as well. Now it gets interesting, right? So now, if we take the energy down to 1, we get a very special orbit. Whenever fixed points form or get destroyed, it's a special orbit. This particular one, we can now actually plot as well. So we do the same method, basically, this maximum energy times 2 square roots. We put those dots in. But over here, at these special points, V is 0, because E minus the potential is 0, and so you have there. So what you're going to do is have it come here. You know it's a tangent, so you know there's an arrow it must go out horizontally. It comes down, but here is a unique point where it doesn't actually obey that. Over here, this very special point, it's going to go in according to the linearized vector, and it's going to go out according to the linearized vector. So when you plot that one, it does that. Okay. It's also the point at which it hits the saddle, right? Because you have a fixed point over there, you basically, and you've shown that it's a saddle, you're now using both the potential as well as your linearized knowledge to plot this orbit. Okay, and then from the bottom, you just get the next one by symmetry. And this, what solution is this? Look where the theta is, right? At pi and minus pi. So this is the solution where you have your pendulum swinging, and then it goes there and it stands still. Okay? Right, and that's an unstable point. So it can do one of two things now when it's over here. It comes in. It can either stand still, come to a dead stop, and then the wind blows, and then it just keeps going, in which case it will make another loop right around, and it'll come back to there. Or it can stand still, and something can knock it back, and then it can start swing backstroke, and can go around the other way, which actually corresponds to this solution sort of running around here, over there. So it's a very unstable solution, which is what a saddle is, but it does show you directly how you have the two possibilities. Once you get to that unstable point, you can either go on or you can go back, and you can see how those two possibilities work by simply the arrows that go out, or the unstable manifold of your saddle. Okay, so it always comes in via the stable manifold, and it goes out with one of the two unstable manifolds if you even blow on it. Okay, so that orbit, just another thing here, this very special orbit that's going to make the difference between it swinging around like that and it doing this type of motion back and forth, is, we call it the heteroclinic orbit. There are two dramatically different states of the solution. It's the heteroclinic orbit, and it's characterized by the fact that your heteroclinic orbit also connects two fixed points like this. Okay. If you remember the double well potential, we had the case where we had a fixed point, it came back to itself. We called that the homoclinic orbit. So homo is one, hetero is many, so here it connects many fixed points. What you do next is let's drop the energy even further. Okay, so this thing then is also, we do the same thing, we work out the maximum distance. There those points are, so that distance, that distance, that distance. And now we work out these fixed points because V is a real number, right? So your E, to get a solution, your E must always lie above the potential because you need this thing under the thing to be positive. So the solution is only going to go from this fixed point, from this maximum value of V to 0, and then it's going to go back. Okay, so we need to put in all these 0 points, or the intersections with the potential. So let's do that. There they go. And so now we know when we draw this thing, we start, say, at this point, or any one of them. We start at this point, we move around, we can't cross any of these other trajectories. We hit 0 over there where we're going straight down, and then we move around that way. So there we go, we hit 0, we continue around, and we do that. Okay, and then for the other trajectories, you can draw them as well. And there they are. Now I'm actually managing to put in the arrows. And you can see that thing, the circle, actually corresponds to the pendulum doing this, just tick-tocking back and forth. The next one, E equals to 0, is on the axes. I just picked these E's so that there was analytic solutions for where it would hit it, right? Because if E is a half, then theta, you can work out this theta, it's 2 over 3. Pi. You know those analytics. Whenever I work with cos and I have to draw potential or trigonometric functions, and I have to draw these lines, I pick them so that I can actually get the analytic values out. You can pick any one, but it's just easier if I pick a half because I know easily how to invert cos theta equals to a half. Okay, 0 is also easy because I know the zeros are then at 3 pi over 2 and pi over 2 plus or minus. Okay, so there I draw it. I once again draw the maximum values. I draw the zeros where it's going to hit my axes. I'll put them all in, and then I have all I need to actually put in the trajectories, and there they go. And you can see that even though this thing looked like a squashed pancake, the moment we move away from the saddle, it's becoming more and more spherical. Just one more, minus 0.5, you do the same thing, you draw the maximum, you draw the intercepts on the axes, and then you put in the trajectories, and you're done. So you can actually see now how this thing becomes more and more spherical, and you can see the lowest value that E can have is minus 1. If E is less than minus 1, you have no solution. Okay? And E equals to minus 1 corresponds to these fixed points. They're just the stationary points over there. Okay. Right, so that's the general phase diagram. Just a few things that we've learned from it. One, just the definition of our heteroclinic orbit, which is that red orbit. They also sometimes call it a saddle connection. It's later going to play an exceedingly important role in when chaos starts, because chaos starts when you start moving around that saddle connection. Okay, it's an orbit that starts and finishes at different fixed points. It connects the unstable manifold of the saddle, in other words, the arrow that goes out of the saddle, to the stable manifold of the saddle of another saddle. That's the arrow that comes in, and for the pendulum, this occurs when E equals to 1. Okay, so there it is. It's connecting the unstable part of the saddle to the stable part of the saddle at pi, and here it's connecting the unstable part of the saddle at pi to the stable part of the saddle at minus pi. Okay, so just to write what I said but didn't write on the previous slide, here you have the whirling motion that's very dangerous for your hand. Here you have the whirling motion in the other anti-clockwise direction, which is very dangerous for the other hand. And then you have the librations, or some people call them oscillations, in between. And this is generally true. These heteroclinic orbits tend to differentiate two types of solutions almost always when you find them. So often the first thing I actually plot is this orbit where I have my energy hitting the maximum of the turning points of my potential. And you can actually do that in your problem set as well. Now what I'm going to do is I'm going to add damping. So the reason why we study complex systems, even though they are a subset of all possible systems, is the same reason in mechanics. We have this idealized idea of a frictionless system. In other words, you have this double well potential, you put the ball in, and the ball goes up, hits the same height, and the ball comes back. In practice, this never happens, right? Because heat sucks energy out of the system, and the thing goes up, doesn't get quite as high, and it slowly goes until it eventually is going to get stuck in one potential. The same is true with your pendulum. We can have the pendulum going round, round and round and round, but we all know eventually there's a little bit of friction here at the pivot, or there's friction with a ball hitting the air, and very slowly the pendulum is going to lose energy and then eventually go tick-tock, and then stop. And in fact, a large problem in mechanics that still exists is people that want to store energy. And one way of doing it is they make a flywheel. And the reason why they want to do this is, right, with solar energy, you get energy when the light shines. But most of our usage of energy is when everybody goes home and baths and puts on their geyser and cooks and stuff. So you actually want to make the energy when the light shines. You want to store it so that you don't have blackouts or you don't have load shedding when you don't have energy. And this is a problem universal. And there's a lot of money that actually goes into how you store energy. And so one way of doing it is you basically have two heavy objects that spin. And so when you have a lot of energy, you spin these objects up. And the ideal thing is you want them to continue spinning and not lose energy due to friction. And then when you need the energy, you put a magnet around it. The thing that spins has magnets. And then when you want to take out the energy, you put a coil around it. And you can then pull out that energy by simply directly making electricity. So they call that a flywheel. There's a lot of research in there. But the main problem with a flywheel is once you spun it up, the friction actually makes you lose energy to the atmosphere rather than being able to extract it later. So the losses when you store energy is something that people are actively working on decreasing. So you might say, let's get back to the math. So we know all our systems dissipate. Why do we study the conservative systems? And the answer is they give us very, very useful tools to actually describe systems that are very close to them. So what we're now going to do is we're going to put in a smaller amount of damping, and we're going to see what effect that has and how we plot the phase diagram for that. Okay, so we put in a small amount of damping. So our new equation is basically this one, theta double dot minus b times theta dot plus sine theta, and b is greater than 0, so in other words, it's sucking energy out, and we call it the damping strength, or the dimensionless damping strength. And then what we have, and what we're going to see, I'm basically going to illustrate how this happens, is that the centers, basically the thing which is vibrating around, eventually become spirals, because the pendulum goes tick-tock, and eventually stops. So the amplitude of the thing decreases, and that's exactly what a spiral is. And the saddles, they still remain. Okay, it's a property of what happens, but I'll prove this to you when we get it. Okay, so we're now going to analyze that system, and then we can actually see how we plot the phase diagram. So the linear analysis is pretty much straightforward. We write it in a first order form. We are going to introduce our energy. Okay, we now know that we don't have a potential system, okay, because I've told you that we're going to get stable spirals, and we know that it's not a conservative system does not have stable spirals. But we still have this idea of energy. We can always say that it's just, we make this function, we call it that, okay. The question we're now going to ask is, how does this change along a trajectory? In other words, we want to work out dE dot, and we do that. And the same technique as we've done previously, you just work out dd tau of this thing, so it's simply vv dot plus sine theta is theta dot. But instead of replacing the damping free equations, we're now going to replace these full equations in there. And what we then get is that, if I substitute it, and then I simplify it, it's just minus bv squared. So if b is 0, it's 0 change, and we remain the energy, constant energy surfaces or trajectories are the contours or the trajectories. But in this case, what we've basically proven is that the energy change is equals to minus b times v squared. We've defined b for this problem to be positive, because it's positive damping, we just lose energy. And so that's always less than 0. So we know that along a trajectory, this E, this energy, is going to decrease, which we expect because the damping is sucking the energy out. And so there's a monotonic decrease of energy. okay, for any given trajectory. So you must remember that, okay? So if you have a whole bunch of energy contours, any trajectory in a damped system is going to go from contour to contour such that the value of energy on that contour decreases. Okay, so now let's use that to actually draw the phase portrait for the damped system. So there's our linear equations, there's the fixed points we can work out, they remain unchanged. So the same fixed points for the damped and the undamped. We can linearize. The only thing that now changes is that this ddv is no longer 0, but it's equals to minus b. We once again work out the determinant, which is simply cos theta star, so it's minus 1. So again, our fixed points, the saddles basically remain saddles, but the trace now is minus b. Okay, and that trace, because it's negative, immediately tells you that if the determinant is positive, namely that we have centers, the trace is negative, so the amplitude is going to decrease. So I've proved to you that we have spirals, and therefore it's not a conservative system if B is positive. Let's now just remind you, this is the one that we just derived in precariously painful detail in the previous slide. And for the conservative system, the B equals to 0 case. What I now want to do is I actually want to use that to plot the solution for the damping case where B equals to 0.1. Okay, so what I've done to be able to actually plot the thing for the damping case for B equals to 0.1 is I've taken these contours, which are my energy contours, right? These lines over here are no longer the trajectories. I've just put them in the background because I know the trajectories I have to draw have to systematically move over these contours. Okay. What I've also done is I've plotted these vector fields are in fact the vector fields that come from this differential equation, but this line over here of theta equals to minus pi is no longer a null line. Okay, and you can see it's no longer a null line because you see these arrows are not horizontal. They're actually pointing down, and they're pointing down because you have this minus BV term extra coming in there. Okay, so these are not null lines, but I've just plotted the same arrows for the damped case as what I've plotted for the undamped case that you can see. Over here, the one on this axis, you can see this line is in fact a null line because when theta dot is equals to 0 when v is equals to 0, and the arrows are exactly vertical, so this one is in fact a null line. And so what I now want to do is plot trajectories for this particular case using that I know the trajectory is slowly going to decrease along these potentials. In fact, it can only go down the potential, it can never climb up. Okay, so I just want to go on a little bit with my linear analysis to prove to you that we have spirals. If n is even, you have stable spirals because the determinant is positive and b is greater than 0. Okay, if n is odd, you have saddles because the determinant is negative. But the only thing is that the Eigen Directions now differ very, very slightly from the case where b is equals to 0. So these arrows over here are no longer going to be 1, 1, and minus 1 like the previous case. They're going to move, but very, very little, by like 0.1. Okay, and you can work out the Eigen Directions directly from this matrix. Okay, the null clines that I've said, this one on the axis is right, but the null cline for the v dot equals to 0 is basically sine theta over b. So they're going to be close to these lines, but they're going to move backwards a bit over here. If you actually plot that in, I haven't done so. Now, the final thing, in the last 3 minutes, I'm going to draw the trajectories for you. Okay, so let's now draw the trajectories. Okay, and I'm simply going to use the fact that I know the thing is almost the same as a contour, but whenever I reach a contour, it's going to cross the contour, but it'll never go back about it. So you can see I can draw start trajectory up here. It sort of sticks to a contour, then is going to cross it slowly, is going to stick to it, and it's sort of going to follow the contours. Right? So you can see here it's decreasing, and eventually it hits this top, what's it, 1.8. energy over there. It's going to cross it, but then it's going to stick very, very close to it. Right? It's going to slowly depart from it. And in fact, it departs, the closest it gets to the v equals to 0, the closer it sticks to the contours. So over here, it's once again going to follow this thing. It's going to make the turn with it, going to cross it over there, but slowly sort of stick to it, and then it's going to leave. Okay, so you can see how we can actually get an idea of what these contours are, the actual trajectory, by simply having plotted the conservative system in the background. Let's pick another one. Okay, so this thing is going to decrease, and eventually, as the energy decreases, you're going to have a contour that starts somewhere, sort of follows the trajectories, and eventually hits the saddle. Okay, so you basically have, this is basically the example. Watch the thing. The thing is spinning very fast, and then as it loses energy, it spins slower and slower and slower, and eventually it gets there and it gets stuck. And then once again, it has two choices. It can either be pushed a little bit that way, and then do that, or it can be up here and be pushed a little bit this way, and it can do this. And these two solutions you have, so there's the one that sort of just carries on going, okay, and it's going to make a spiral around that pi over 2. The other one can go the other way, and there you can see it's once again continues to cross the equipotential lines, and it's going to go around, and eventually it's going to spiral in. Oops, sorry. Okay. If you take a one that's lower than this one that hits the saddle, it's automatically going to go in here. Okay. And so this is basically the phase portrait of the dam system that you've drawn using the conservative potential that you started with. Okay, so the conservative potential plays an exceedingly important role in understanding more phase diagrams. Another crucial point is a very important thing of choosing which fixed point it goes to is where it hits the saddle, right? These trajectories that actually hit the saddle, I actually drew these by starting at the saddle and then going a little bit out along the Eigen direction and then putting it forward, and then starting at the saddle, going a little bit out here, and then integrating backwards to actually get this point, because this is the transition point. The saddle connection in these systems that you perturb off of a potential of a conservative system is crucially important. Okay, the centers either become stable spirals or unstable spirals, but the saddle is actually going to dictate which spiral it chooses, or a solution, chooses to go into. That's all for me. Questions? Okay. See you on Tuesday. And just remember, for whoever